This is Janet and Rabia.
Welcome to Everest Physics Academy.
Before we start, we'd like to recommend our Everest Physics books for high school,
where you can find more explanations and solve applications and problems.
In this video, we will explain the amplitude and the pseudo-period of free damped oscillations. Determine the differential equation that governs the damped oscillations of a horizontal elastic pendulum using the expression of the mechanical energy and Newton's second law. Introduce the solution of differential equation, and finally discuss the effect of the damping coefficient on the oscillations.
Now let's start with the amplitude and the period of free damped mechanical oscillations of a horizontal elastic pendulum. Consider this spring block system. The block is shifted from its equilibrium position O and then it is released from rest. Observe the oscillations. This type of oscillations is called free damped mechanical oscillations. Now let's talk about the amplitude. It was 40 centimeters at the beginning, and then it becomes 15 centimeters, and then 10 centimeters. So the object oscillates with a decreasing amplitude. Now let's talk about the period. The object oscillates with a period called the pseudo-period T. The oscillations are said to be pseudo-periodic, which means that they are repeated during the same time interval, but not identically. So we have the xt graph of our damped oscillator, and we draw the xt graph of the same oscillator in case friction is negligible. Comparing the two curves shows that t is greater than the natural period t0. Therefore, the natural period is the minimum possible period of free oscillations. Now, let's move to the effect of friction on the value of the pseudo-period. The smaller the friction is, the closer is the pseudo-period to the natural period. Now, look at the curves. The pseudo-period is slightly greater than the natural period, so we can conclude that our oscillator is slightly damped. Now, in solving problems, if friction is very small, which is the case of slight damping, then you can replace T by T0 because T is approximately equal to T0.
Differential equation of the motion. In damped oscillations, we study the type of the friction force having the form F equal minus hv, where h is a positive constant called the damping coefficient. H depends on many factors, such as the surface area of the object, the form of the surface of the object, the nature of the medium, etc. V is the velocity of the center of mass of the object. Since we have friction, the mechanical energy now is no more conserved or no more constant, and so its time derivative does not equal to zero. It is equal to the power of the friction. But the power of the friction can be given by this formula, F scalar V or F dot V. Replacing F by minus HV, this is going to be minus HV scalar V. But V scalar V is equal to V squared, so P or the power of the friction is equal to minus HV squared. Therefore, the time derivative of the mechanical energy is equal to minus HV squared. Let's write the expression of the mechanical energy in the system, which is equal to 1/2 mv squared plus 1/2 kx squared. Differentiate both sides with respect to time. So the derivative of the mechanical energy with respect to time is equal to into 1/2 mv v prime plus 2 into 1/2 kx x prime. But dme by dt is equal to minus hv squared. So 2 times half is equal to 1, and this term 2 times half is equal to 1. Remove or move minus hv squared from the right side to the left side, we get a new relation, which is mv v prime plus hv squared plus kx v is equal to 0. In each of these three terms, we have v. So we can take v as a common factor. Rearrange. So v into mx double prime, x double prime is equal to v prime. And x prime is equal to v. So we have v into mx double prime plus h x prime plus kx is equal to 0. As you know, v equal to 0 is rejected, cannot be taken as a solution. Therefore, mx double prime plus hx prime plus kx is equal to 0. Divide both sides by m, we get the differential equation or the second order differential equation.
Focus, please. This is important.
Now, let's determine the differential equation using Newton's second law. Our system is the block. The external forces acting on the block are its weight mg, the normal force exerted by the surface, the restoring force, the friction force. You observe that we do not draw the restoring force and the friction force on the figure because these forces reverse direction each half oscillation. Now let's move to Newton's second law. Sigma F external is equal to ma. This is going to be mg plus n plus t plus f is equal to ma. Recall that the expressions of the spring force and the friction force are T is equal minus Kxi and F is equal to minus HVi. Now let's project the vectors of this equation along the x-axis. Let's start with the weight and the normal force. These forces are vertical, so they do not have components along the x-axis. Now, the spring force becomes minus Kx and the friction force becomes minus Hv. Rearrange. 0 is equal to Kx plus Hv plus mx double prime. Recall that v is equal to x prime. So we will replace v in this equation by x prime. And then we divide by m, and this is our differential equation. X double prime plus h over mx plus k over mx is equal to 0.
Time equation of the motion of the block. This symbol means this topic is outside our curriculum. It is an extra study or extra information. In the previous slide, we proved that the differential equation in case of free damping is given by x double prime plus h over mx prime plus k over mx is equal to 0. Under damped mechanical oscillator, it is one of the three cases of damping. In this video, we are going to study only this case of damping. In this case, h over 2m is less than the square root of k over m, and so the oscillator is said to be under damped. The solution of the obtained differential equation in this case is given by x equal a exponential minus ht over 2m sine omega t plus phi, or x equal a exponential minus ht over 2m cosine omega t plus another phi. The constants a and the two values of phi are determined from the initial conditions x0 and v0. The amplitude of the abscissa x is not constant. The values of the amplitude of the abscissa x belong to a curve whose equation is given by xm of 0 e to the power minus ht over 2m, where xm of 0 is the initial amplitude of x. And we conclude that the values of the amplitude belong to a curve decreases exponentially with time. Now, expression of omega. Omega is equal to the square root of omega 0 squared minus h over 2m squared, where omega 0 is the natural angular frequency, and it is equal to the square root of k over m. The value of omega gives the value of the pseudo-period according to this relation. The pseudo-period t is equal to 2 pi over omega. This expression of omega says that as h increases, omega decreases. And we have t equal to pi over omega. Since omega is in the denominator, so as the denominator decreases, the quotient increases. So we can conclude that the pseudo-period increases with the value of h. The expression of omega also says that omega is less than omega 0. Observe this equation. Omega equal to the square root of omega 0 squared minus this term. So omega is always less than omega 0. But t equal to pi over omega and t0 equal to pi over omega 0. Since omega is less than omega 0, so we can conclude that t greater than t0, or the pseudo period is greater than the natural period. The expression of omega also says that for h equals 0 in this equation, so omega is equal to the square root of omega 0 squared. So omega is equal to omega 0. So we have a free undamped mechanical oscillation. For this case, if h over 2m is much less than the square root of k over m, the oscillations are said to be slightly damped. What do we mean by slightly damped? In slightly damped, the oscillator performs many oscillations before it stops. And finally, let's study this case. If h over 2m is slightly less than the square root of k over m, the oscillations are said to be heavily damped. Now, what do we mean by heavily damped? The oscillator performs a few oscillations, or it does not complete one oscillation before it stops. Thank you for watching. If you like this video,
Subscribe to the channel, hit the like button and share.